We live at the bottom of an ocean of gas. But for most of human history, people seem to be blissfully unaware of the gases swirling around them. I mean, they were obviously aware of the air, but not about individual gases as we know them today. From burning wood to boiling water, fermenting plants, alchemical reactions, even exhaling. All of these processes release gases, so why did it take so long for humans to really take notice of any of them? The brilliant Scottish chemist Sir William Ramsay, discoverer of the noble gases, summarized how the ancients viewed various gases in his book, The Gases of the Atmosphere, where he said, "It had not escaped observation that air obtained by distilling animal and vegetable matter or by the action of acids on iron and zinc differed from ordinary air by being inflammable, but such airs were regarded as atmospheric air modified in some manner, as it is modified when perfumed." So the concept of different gases didn't really exist. All gases were just different forms of atmospheric air with its properties tweaked. For example, some airs helped with combustion while others prevented combustion. But why did people only think in terms of air? Well, there's a simple answer for that: the classical elements. For over 2,000 years, most philosophers thought that all of the matter around us was made of varying proportions of earth, fire, water, and air. In Western philosophy, these ideas emerged in ancient Greece thanks to the writings of Empedocles and Aristotle, hence the common name of the Aristotelian elements. But Eastern philosophies in ancient India were very similar. Regardless of where the idea first emerged, and despite there being several variations of this concept throughout history, the pervasive idea that air was an element with modifiable properties meant that people just didn't really think of gases as anything other than, well, air. That all changed in the mid-1600s thanks to a Flemish chemist called Jan Baptist van Helmont. Van Helmont was a great experimenter who regularly took precise mass measurements throughout his investigations, which is something that wasn't very common at the time. A good example of this was in the experiment that he's most famous for, the willow tree experiment. Here, he weighed out some soil, then planted a willow tree in it. After 5 years of giving the tree nothing but water, he measured the weight of the tree, finding it to be 164 pounds or 74 kilograms, but the weight of the soil had barely changed. From this experiment, he concluded that the tree was made from water alone, and that the element known as earth wasn't actually an element at all, as it could in essence be reduced to water. In the book A History of Chemistry by Ernst von Meyer, he says, "With respect to air, it is uncertain whether Van Helmont looked upon it as an element or not. He denied altogether that fire could be of a material nature, which is evidence of his extraordinary clearness of perception." So one thing that we can be sure of is that Van Helmont did not blindly conform to a belief in the Aristotelian elements. This allowed him to look at so-called airs from a more curious and critical viewpoint compared to many of his predecessors. And that's exactly what he did. For example, he performed an experiment where he burnt charcoal inside a closed vessel, and noticed that the weight of the ash was significantly less than the weight of the charcoal he had started with. Van Helmont explained this by saying that some of the charcoal had escaped in the form of an invisible substance. Van Helmont needed a name for his invisible substance. Due to its intangible nature, he named it after the Greek word associated with the primordial void from which all creation happened, chaos, which in Greek is chaos, giving him the word gas. This particular gas Van Helmont called gas sylvestre, meaning wild gas. In Ramsay's book, he says, Van Helmont was acquainted with various kinds of gases, as appears from his treatise, De Flatibus. His gas sylvestre was evolved from fermenting liquors, and he knew that it was formed during the combustion of charcoal, and also that it was present in the Grotto del Canne near Naples. By the way, just a quick aside on this Grotto del Canne, or Cave of Dogs. This place was given its name because of the high levels of volcanic gases which can cause any dogs who enter to faint or even to suffocate, while humans would be unaffected, since the gases are denser than regular air, so they sink to the bottom. It was considered a tourist attraction back in the 17th century. The Dutch artist Cornelis de Bruyn visited the cave in 1677 and wrote, "Next, one comes close to the road by a small cave called Grotto del Canne, which is very venomous to the extent that if a dog is kept inside, it dies very quickly. I had the curiosity to visit it with 2 different dogs and found that when the animal remains standing on its legs, it is not harmed by the poison. However, if one forcibly presses it down, it quickly loses its strength after great struggling and desperate resistance, and would undoubtedly die in an instant if not promptly picked up and thrown into a nearby water or lake, where it immediately recovers but with some dizziness, walking like a human who is completely drunk. This lake has the same nature as the cave and boils in several places due to the great heat of sulfur. Curiosity drove me to investigate how high the venom in the cave might be from the ground, so bowing my head downward, I found it to be only 1 foot high from the ground. A quick note here, I hope it goes without saying, but that is not the kind of experiment that you should try and repeat. Going back to Van Helmont, his work was groundbreaking and it should have opened the doors into a whole new world of chemistry, but it didn't. All thanks to a brand new theory of combustion which, shortly after Van Helmont's death, quickly became widely accepted amongst the scientific community. A theory known as Phlogiston theory. Now, I already have an entire video all about Phlogiston theory, which I'll link below if you want the full story, but here's the gist. According to Phlogiston theory, all combustible substances contain a fire element called phlogiston, which is released when the substance burns. So, for example, if you intensely heat a metal, today we understand that it reacts with oxygen in the air to form a metal oxide, the old name for which was a calx. However, according to phlogiston theory, what's actually happening is that the metal is not an element but a compound that consists of phlogiston and the calx. And when it burns, the phlogiston is released, leaving only the calx behind. So, rather than oxygen being added to burning things, phlogiston was escaping. The phlogiston could then be restored to the calx to reproduce the metal by heating the calx with something high in phlogiston, like charcoal. Today we understand that it's actually the oxygen from the metal oxide that's reacting with the carbon in the charcoal. The whole theory was the complete opposite of how we understand combustion today, and it was full of inconsistencies which eventually led to its downfall. According to Ramsay, the influence of the phlogistic theory on the knowledge of the nature of air was of such a kind as to retard its progress. For how could that knowledge be furthered when the most active constituent of air was represented by a negation? This backwards theory may have set back our understanding of the air by around 100 years. Even the word gas fell by the wayside as chemists instead referred to phlogisticated air or dephlogisticated air. In the mid-1700s, a full century after Van Helmont's work, a Scottish medical student in his early 20s called Joseph Black was working on his doctoral thesis. He was looking into possible remedies for kidney stones and began investigating quicklime, today known better as calcium oxide. It was well known at the time that you can easily prepare quicklime just by heating limestone. Simple. Early in his experiments, Black discovered that when you do this, the mass of the quicklime produced is significantly less than the mass of the limestone you started with. This suggested that the limestone lost something when it turned into quicklime. An air was released, to use the old terminology. He wondered if you could trap this air, and did so by performing the reaction in a closed container. He then took this container and placed a fresh piece of lime inside. Not the fruit, I'm referring to lime as in a mixture of calcium oxides and hydroxides. Then he confined the 2 substances over water and waited to see what happened. He watched as the water slowly rose up inside the container. It appeared that the lime was reacting with and absorbing the air that he had trapped. Sure enough, when he removed the lime, it had lost a lot of its caustic or corrosive properties, almost as if it was turning back into limestone. Similarly, he was able to show that the air could turn a solution of lime, also known as lime water, back into limestone because shaking the 2 together caused the solution to turn cloudy, meaning a precipitate of limestone began to form. Now, this was unlike anything he had seen before. He was seemingly able to trap a unique air and use it for chemical reactions. What was this stuff? Black measured the weight lost by the limestone when it was heated and compared it to the weight lost by the limestone when it was reacted with acids and found the differences to be the same. It seemed that you could release this air in multiple ways. He performed similar experiments on magnesium alba, which is chemically similar to limestone, and found that the same air could be obtained from it as well. Because this air was found fixed in substances such as these, Black gave it the name fixed air. He was able to demonstrate that fixed air was heavier than atmospheric air by his ability to pour it from one vessel to another, then over a candle to extinguish the flame, which also showed that it did not support combustion. In addition, he found that fixed air is fatal to animal life, and that it was slightly acidic when dissolved in water. In his writings, he also mentioned how fixed air is the same as the air found in the Grotto del Canne, how it's produced by fermentation, by burning charcoal, and even by exhaling. He proved this by shaking each air with lime water and observing that they all turned it cloudy in the same way. He even showed that fixed air is found in atmospheric air by leaving lime water exposed to the atmosphere for a long period and observing a thin, cloudy layer forming on the surface. Thanks to Black, chemists learnt a lot about fixed air. All of this work happened in the very early days of the Industrial Revolution. Our species has achieved some magnificent things in the past 250 years, but it's caused a lot of damage as well. The good thing is that we're more aware of these issues than ever, and we have the ability to come together as a community to make things better, which is exactly what my friends at Planet Wild are all about. They are a community crowdfunding for nature protection. It's why I'm so happy to be partnering with them. If you haven't heard of them before, they have a really unique approach to conservation. Each month, they partner with a different conservation organization to help them complete a specific project. When you or I become a member of Planet Wild, our contributions go directly to the project. But here's where it gets really cool. Planet Wild has their own YouTube channel, where they share beautifully produced and educational videos about the projects that they support, so you get to see the direct effects of your membership. They've already participated in some amazing projects, such as using chainsaw detectors to protect one of the last old-growth forests in Europe, or rebuilding habitats for lemurs in Madagascar. If you're like me and you love the great outdoors but feel powerless to improve things yourself, Planet Wild is a fantastic option. As a member, it's been great feeling like an active participant in the kinds of projects that Planet Wild supports around the world. You can give whatever amount feels right to you. The membership can start from as little as the price of a sandwich. Also, if you use my code Chemistorian11, you'll get a free month paid for by me, so you can check them out and see for yourself how great they are. And there's no catch here, you can cancel at any time. If you want to see them in action, watch their video using chainsaw detectors to protect old-growth forests. We're the only species with the power to make changes on the scale that we need. Let's protect our planet by working together. Okay, back to the video. Okay, now let me show you something really cool. This is the oldest book in my collection. Elementary Lectures on Chemistry and Natural History by Antoine Fourcroy. It was published in 1785, during the lifetime of Joseph Black. By the time this book was published, a handful of different airs were known. Let's take a look at the description of Black's fixed air. There is another kind of air very different from this in all its characteristic properties. It destroys animals, extinguishes flame, and prevents the calcination of metals. This air is called fixed air, and more recently has been distinguished by the name of aerial acid, from a certain resemblance to the common acids in the effects which it produces, though it has never yet been obtained in a concrete form. But whatever may be its true constitution, we find it of great importance in the economy of nature. Many of the hardest bodies, all animal and vegetable substances, contain a large quantity of this air. Limestone and the alkaline salts owe nearly 1/2 of their weight to its presence in their composition, and when it is expelled by heat, they both of them become caustic. It is emitted in great abundance from the crevices of subterraneous cavities, where it forms what is called the choke damp of mines. This choke damp floats at the bottom under the common air on account of a more considerable specific gravity, and in this way forms a distinct stratum. Fermenting liquors also emit large quantities of it. It is the separation of this air which communicates the sparkling appearance to all liquors and to some mineral waters. The impregnation gives an acid taste to water which instantly flies off when it is uncovered on account of the volatility of the air. It is the presence of this air which enables water to dissolve the earths and metals, a property that water instantly loses when the air is dispelled. The specific gravity, the attraction for water for alkalis and earths, distinguish this aerial fluid from all others. Whether it be a true primitive substance or only a compound of imperial air with some other principle is a question not proper to discuss here. On that last point, in 1778, just 7 years before this book was published, the French chemist Antoine Lavoisier published some important work. As Ramsay summarized in his book, in this he describes experiments showing that when metallic calces are converted into metals by heating with charcoal, a quantity of fixed air is expelled. And here, for the first time, he points out that fixed air is a compound of carbon with the elastic fluid contained in the calx. Now, if you've watched my phlogiston video, you'll know that the element that Lavoisier was referring to here is what will soon become known as oxygen. So, shortly after this, it was understood that fixed air was a compound of carbon and oxygen, and it rapidly picked up a new name, carbonic acid. In 1856, an American scientist called Eunice Foote performed an interesting experiment. She took 2 glass cylinders with thermometers inside them and connected them together with an air pump. She then used the pump to evacuate the air from one cylinder and compress it into the second. Once both cylinders reached the same starting temperature, she placed them in the shade and later in the sun to see how sunlight heated the air. We can see that the temperature increased in both the exhausted tube and the condensed tube when placed in direct sunlight, but out of the two, the condensed tube got significantly hotter, suggesting that air is able to absorb the sun's rays. She repeated the experiment to compare different gases such as dry air and moist air, but here was her greatest finding. As she wrote in her paper, "The highest effect of the sun's rays I have found to be in carbonic acid gas. When comparing carbonic acid to regular air, she found that it increased in temperature the most when left in the sun." She said, "An atmosphere of that gas would give to our Earth a high temperature, and if, as some suppose, at one period of its history the air had mixed with it a larger proportion than at present, an increased temperature from its own action as well as from increased weight must have necessarily resulted. On comparing the sun's heat in different gases, I found it to be in hydrogen gas 104 degrees, in common air 106 degrees, in oxygen gas 108 degrees, and in carbonic acid 125 degrees. Foote was the first scientist to demonstrate experimentally that carbonic acid was particularly good at absorbing heat from the sun's rays. 3 years later, in 1859, the Irish chemist John Tyndall began investigating the effect of passing infrared radiation through different gases. Here's how the apparatus worked. He took a 4-foot brass tube which was sealed at both ends and connected it to an air pump so that all of the air could be pumped out. At one end of the tube he had a box filled with water which he kept at a constant boil with a gas lamp underneath. A circular window was cut into this box to allow infrared radiation to shine down the tube. An identical box was placed at the opposite end for comparison. To make sure that only heat from infrared radiation was passing into the tube without any heat from conduction, another box was placed in between the boiling water and the tube, which was cooled by a constant flow of cold water. Infrared radiation from both ends shone onto a central thermoelectric pile, which provided a current when exposed to heat. A connected galvanometer contained a needle which would move to show which side was providing the largest current. The screen to the left could be adjusted to calibrate the apparatus so that the needle was at 0 before introducing any gases. The gas that was being investigated was stored in a container and would pass through various pipes that contained chemicals to remove any moisture before passing into the brass tube. Then, as Tyndall said, when the required quantity of gas had been admitted, the galvanometer was observed, and from the deflection of its needle, the absorption was accurately determined. So, the absorption of infrared by different gases in the tube caused a reduction of heat energy on one side of the thermoelectric pile compared to the reference on the other side, and this could be measured precisely by the difference in current. With this apparatus, he found that the absorption by carbonic acid is about 150 times that of oxygen. In another publication, Tyndall wrote about the sun's heat entering the atmosphere and said that when the heat is absorbed by the planet, it is so changed in quality that the rays emanating from the planet cannot get with the same freedom back into space. Thus, the atmosphere admits of the entrance of solar heat, but checks its exit. and the result is a tendency to accumulate heat at the surface of the planet. This is a phenomenon that today we call the greenhouse effect. In 1896, the Swedish chemist Svante Arrhenius published work where he performed a load of calculations to establish the relationship between the amount of carbonic acid in the atmosphere and the temperature of the atmosphere. He used his equations to explain how variations in carbonic acid levels in the atmosphere throughout history could explain why the Earth has gone through various temperate eras and ice ages. At one point he said, "A simple calculation shows that the temperature in the Arctic regions would rise about 8 to 9 degrees C if the carbonic acid increased to 2.5 or 3 times its present value." By this point, I'm sure most of you have figured out the modern name for fixed air or carbonic acid. It's carbon dioxide, probably the most talked about gas in all of human history. Over the next couple of decades, scientists began to connect the dots between the vast amount of carbon dioxide that our post-industrial world was pumping into the atmosphere and the potential for climate change in the future. Check out this article from the New Zealand newspaper, the Rodney and Otamatea Times, published on Wednesday the 14th of August 1912. The furnaces of the world are now burning about 2 billion tons of coal a year. When this is burned, uniting with oxygen, it adds about 7 billion tons of carbon dioxide to the atmosphere yearly. This tends to make the air a more effective blanket for the Earth and to raise its temperature. The effect may be considerable in a few centuries. Little did they know, the effect would be considerable within the same century. In 1958, an American climate scientist called Charles David Keeling received the funding to set up an atmospheric monitoring station on a Hawaiian volcano called Mauna Loa, 3,000 meters above sea level. Keeling found that there seemed to be seasonal variations in atmospheric carbon dioxide levels. As plants die off in the northern hemisphere's autumn and winter, the CO2 concentration increases since there are fewer plants to absorb it. As they grow back in the spring and summer, the CO2 concentration drops back down again. Pretty cool. But what was really interesting was how the average CO2 concentration changed over time. Keeling continued to monitor the levels for years, decades. He passed away in 2005, but the measurements continued. This graph became known as the Keeling Curve, and what it shows is astonishing. From an initial concentration in 1958 of 313 parts per million, the CO2 concentration has steadily increased year by year until it finally passed 400 parts per million in 2013. Scientists estimated that it was the first time that atmospheric CO2 had been at those levels for at least 2 million years. It happened fast, and it's only continued to rise since. This website plots the average surface air temperature of the planet, with data from every single day from January 1940 to the present. I'll link the website in the description if you'd like to check it out for yourself. It's clear from this data that the average global temperatures are rising. If we hide all the data from 1940 to 1990, we're left with all of the hottest years on record. Our atmosphere's CO2 levels are increasing and the planet is getting hotter. As a result, the ice caps are melting, sea levels are rising, extreme weather events are becoming more common, droughts and wildfires continue to spread. Today, most scientists agree that human activities since the Industrial Revolution have caused this. But it's not too late. We're at a critical time in history. What we need is to be using renewable energy sources rather than burning fossil fuels. According to the International Energy Agency, global renewable electricity generation is forecast to climb to over 17,000 terawatt-hours by the end of this decade, an increase of almost 90% from 2023. This would be enough to meet the combined power demand of China and the United States in 2030. They also said that this year, in 2025, renewables-based electricity generation is set to overtake coal-fired generation. We've come a long way as a society and we're doing much better. It is not impossible to fix our planet. We just need to actually try. Thanks again to Planet Wild for partnering with me for this video. Remember to use my code to get a month's membership for free. It's a great cause and you won't regret it. If you want to see them in action, watch their video on protecting old growth forests. Thanks for watching and I'll see you in the next one.